Around 251.9 million years ago, Earth faced its most profound crisis. The boundary between the Permian and Triassic periods marked an extinction event unlike any other, known colloquially as the Great Dying. Life on Earth nearly vanished entirely. This wasn't a single, sudden moment, but a period of intense environmental collapse that spanned tens of thousands of years, wiping out the vast majority of species across the planet. The statistics are staggering, painting a picture of ecological devastation. 81% of marine species perished. On land, the toll was equally grim, with 70% of terrestrial vertebrate species disappearing. Even insects, typically resilient survivors, suffered their greatest known mass extinction. Biological families and genera were decimated, fundamentally restructuring the tree of life for millions of years to come. For decades, scientists debated the cause of this catastrophe. Today, a strong consensus points to one primary culprit: the massive flood basalt volcanic eruptions that formed the Siberian Traps. Located in what is now Siberia, this was one of the largest volcanic events in Earth's history. It wasn't just the lava flows, which covered an area the size of Saudi Arabia. It was the immense volume of gases and other materials released into the atmosphere and oceans. These eruptions were particularly devastating because they didn't just release typical volcanic gases. They intruded upon and ignited thick sequences of coal beds and other carbon-rich sediments underground. This roasting process dramatically amplified the release of greenhouse gases, specifically carbon dioxide and methane. The Siberian Traps unleashed pulses of magma, pushing vast quantities of toxic elements and gases into the environment. The influx of carbon dioxide into the atmosphere was incredibly rapid by geological standards. Estimates suggest atmospheric CO2 levels jumped from around 400 parts per million to 2,500 parts per million, potentially reaching as high as 8,000 parts per million according to some models. This triggered a hyperthermal event, sending global temperatures soaring. Average surface temperatures rose by as much as 18 degrees Celsius in some regions, creating an incredibly hostile climate for life. As the atmosphere absorbed more carbon dioxide, the oceans absorbed it too. This led to widespread ocean acidification, a process where seawater pH drops. Many marine organisms, particularly those with calcium carbonate skeletons or shells, were acutely vulnerable to this chemical shift. Organisms with low metabolic rates and simple respiratory systems, like corals, brachiopods, and calcareous sponges, suffered devastating losses. Those with better oxygen transport and less reliance on calcium carbonate fared slightly better. Simultaneously, the warming oceans became oxygen-starved, a state known as anoxia. In many areas, hydrogen sulfide built up, leading to euxinia sulfidic toxic waters. Evidence for this comes from widespread anoxic sediments and the presence of biomarkers for green sulfur bacteria, which thrive in sunlight-lit sulfidic conditions. This toxic, deoxygenated water expanded, particularly in shallow coastal areas, suffocating marine life. On land, the climate change manifested as widespread aridification. Global warming intensified drying trends, especially across the supercontinent Pangaea. This drying caused a collapse of many plant communities, including the extensive Glossopteris flora in Gondwana. The loss of rooted plants triggered significant soil erosion, changing river systems from meandering to braided patterns, a dramatic visual clue left in the rock record. Volcanic emissions also likely damaged the protective ozone layer. Compounds rich in halogens from the eruptions, along with potentially methane released from sediments, could have severely thinned atmospheric ozone. This would have exposed terrestrial life, particularly plants, to harmful levels of ultraviolet radiation. Fossil plant spores from this time show high rates of mutation and deformities, consistent with increased UVB exposure. The marine extinction was highly selective. Organisms with calcareous hard parts were hit hardest. Trilobites, iconic creatures of the Paleozoic seas, vanished completely. Blastoids and rugose and tabulate corals also failed to survive. Some groups, like crinoids and articulate brachiopods, survived but were drastically reduced in diversity, clinging on with just a few hardy species. Terrestrial vertebrates faced different challenges, primarily drought and temperature extremes. Large herbivores suffered the greatest losses. Synapsids, often called proto-mammals, including large dissonodonts and some therosphalians, were severely impacted. Reptiles also experienced significant declines, although some groups, like the procolophonids and certain diapsids, managed to persist. The loss of so many large animals meant the collapse of complex food webs on land. While volcanism is the leading explanation, other factors have been proposed as potential contributors or triggers. The sudden release of vast amounts of methane from seafloor gas hydrates, or methane clathrates, possibly initiated by warming or volcanic activity, could explain rapid carbon isotope shifts and hyperwarming. The possibility of an asteroid impact has also been explored, though the evidence is weaker, and no definitive impact crater of the right size and age has been confirmed as the primary driver. Recovering from the Great Dying was a slow, arduous process. For marine life, it took millions of years, arguably not reaching pre-extinction diversity until the Middle Jurassic, some 75 million years later. Terrestrial ecosystems lagged even further behind, requiring up to 30 million years to fully rebuild their structure and diversity. This prolonged recovery highlights the scale of the environmental collapse. The seas of the early Triassic were often dominated by disaster taxa, a few widespread, opportunistic species, like the bivalve Claria or the brachiopod Lingularia. Microbial reefs briefly proliferated in the absence of significant competition from complex reef-building animals. Bivalves, relatively minor players before the extinction, diversified rapidly and began to fill ecological roles previously occupied by brachiopods, although it took millions of years for this shift to fully manifest. Marine vertebrates, like early ichthyosaurs, also began to diversify relatively quickly. Plant recovery on land was patchy and prolonged. Forests globally disappeared, replaced by sparse, low-lying vegetation dominated by hardy, opportunistic species, like lycophytes. This period is marked by the coal gap, a puzzling absence of significant coal deposits for millions of years, suggesting the ecosystems capable of forming vast peat swamps were gone. Full recovery of complex woody woodlands took millions of years. Terrestrial vertebrate faunas were initially dominated by survivors, like the Dicynodont Lystrosaurus, which became incredibly abundant, sometimes making up 90% of fossil assemblages. This hardy, pig-sized herbivore was well suited to the harsh, fluctuating conditions. Smaller cynodonts, ancestors of mammals, also survived. The Middle Triassic saw the rise of archosaurs, the group that would eventually give rise to dinosaurs and crocodiles, marking a significant shift in terrestrial dominance. Studying the Permian-Triassic extinction offers a stark warning. The rapid release of greenhouse gases, rising global temperatures, ocean acidification, and oxygen depletion are themes that resonate today. While the geological timescales are vast, the rate of current human-caused carbon emissions may be comparable or even faster than the pulsed emissions that drove the Great Dying. Understanding how Earth systems responded to that ancient catastrophe provides crucial context for the environmental challenges facing our planet now.